Today, we're diving into the really high-stakes world of high-power RF transistor assembly. And believe me, this is a world where the tiniest physical mistakes can completely wreck performance. And where heat? Well, heat is the silent enemy you've always got to be one step ahead of.
So take a look at these. These are air cavity plastic, or ACP packages. Don't let their small size fool you for a second. These things are absolute powerhouses, designed to handle just a massive amount of RF power. But all that power creates a huge challenge. You have to assemble them with near-perfect precision. And that really brings us to the million-dollar question for anyone working in this space, right? How do you actually mount these things correctly so they perform reliably, day in and day out, without just overheating and failing? That's exactly what we're going to break down. Okay, so first things first, let's get to know our building blocks. Because if you don't understand what you're working with, everything else is just guesswork. Right off the bat, you can see a major design choice. Over on the left, we've got the eared package. See those slots? They're there so you can physically bolt the component down. But on the right, you've got the earless version, which is made to be soldered directly onto a heatsink. It's basically two completely different approaches for mounting the same kind of device. And the differences don't stop there. You've also got different materials to think about. On the left is the classic air cavity ceramic, ACC for short. And on the right, you see the more modern air cavity plastic, or ACP. Now, this isn't just about looks. The material directly impacts the thermal properties and, of course, the assembly process itself.
All right, let's talk design. A perfect assembly doesn't just happen at the workbench. No way. It starts way earlier, on the computer with the layout of the printed circuit board. This is literally your blueprint for success.
Now, for a straight lead package like you're seeing in this cross-section, the transistor doesn't just sit on the PCB. It actually sits in it. It's nestled down into a little pocket, a cavity, in the heatsink right below the board. And that makes the depth of that cavity one of the most critical dimensions in the entire assembly. Compare that to gull-wing packages. They're a whole different animal. Their leads are shaped kind of like a gull's wing, hence the name, and they solder right onto pads on the surface of the PCB. So here, the precision isn't about the cavity depth. It's all about getting the design of those pad extensions just right. And this formula, it perfectly captures the challenge. Figuring out the ideal heatsink cavity depth, that's D, isn't about just one number. It's what we call a worst-case tolerance stack-up. You're adding the package standoff to the preform thickness, then subtracting the solder thickness and the gap. And the tricky part is, every single one of those variables has its own tolerance. It's a real puzzle. And here, you can see what those letters actually mean in the real world. ST is the package standoff height, P is the preform, L is the lead solder, G is the gap. When you see it like this visually, the formula just clicks, doesn't it? It really is a delicate balancing act. So just how delicate are we talking? Well, the recommended maximum tolerance for that cavity depth is plus or minus 0.08 millimeters. That is incredibly small. We're talking about the thickness of a single human hair. There is basically zero room for error. Okay, so you've absolutely nailed the design. Now what? Well, now comes the moment of truth, the soldering process. This is where your digital blueprint finally becomes a physical reality. Think of it like a carefully choreographed dance in 5 parts. First, you print the solder paste. Then you place the solder preform, followed by the component itself. After that, it's a trip through the oven for reflow soldering. And finally, inspection to make sure everything went according to plan. The whole thing kicks off with some amazing precision. You have a stencil, which is basically a super precise sheet of metal with little openings, and you lay it over the board. Then a squeegee comes across and applies a perfectly controlled amount of solder paste exactly where it needs to be. And here's the climax of the whole process, the reflow profile. This is not just about cranking up the heat. It's a very precise temperature journey. You start with the preheat phase to activate the flux. Then you see that sharp ramp up to the reflow phase. That's where the solder actually melts. And then a carefully controlled cooling phase makes sure you get a strong, reliable joint. And this is what you're aiming for. When every single step is done just right, you get this, a clean, strong, reliable solder joint. After a final check with an optical inspection, the physical assembly is done. But our story is not over yet. Because now we have to deal with the invisible challenge. We've built the component perfectly, sure, but how do we make sure it survives the incredible amount of heat it's going to generate when it's running? This is all about thermal management. Now, to manage heat, you have to get your head around this term, thermal impedance, or ZFIT. To put it simply, it's a measure of how good the device is at getting rid of heat. It tells you exactly how many degrees the temperature will go up for every single watt of power it's trying to dissipate. Honestly, this is the most important number for predicting how it's going to handle heat. And we can't just cross our fingers and hope for the best. We have to be able to predict performance. And the way we do that is by modeling the thermal behavior using a really clever analogy from the world of electronics. So to model how heat actually flows, we can use a beautiful little analogy, an RC network, just like in an electrical circuit. In these models, electrical resistance stands in for thermal resistance, and capacitance stands in for thermal capacity. The Cauer model on the left is a direct physical translation. Each RC pair you see represents a real layer, like the die, the solder, or the flange. The Foster model on the right, though, is more of a mathematical shortcut. It's an abstraction that's just fitted to match the data we measure. And this really shows you the key difference. The Cauer model actually represents the physical structure. You can probe its internal nodes and see the temperature of a specific layer. The Foster model, on the other hand, is easier to create from measurements, but it's kind of a black box. Its internal nodes don't really correspond to anything real. For system-level simulation, Cauer is definitely the way to go. So why would you go through all this trouble? Because of this right here. These models let you run a simulation and predict, with incredible accuracy, how the junction temperature is going to rise under pulsed power. You can literally see the heat spike with every pulse and then cool down in between. You're basically predicting the future before you even turn the device on for the first time.
So when you step back and look at the whole picture, you realize that the electrical and thermal domains are really just two sides of the same coin. The way you physically build the device, like we saw in the first half, directly controls its thermal performance. And that thermal performance, in turn, impacts its electrical behavior. They are completely linked. And that really brings us to our final thought. As you think about your own work, the big question you have to ask yourself is this: is my design process really connecting the physical build to the thermal reality? Because mastering that connection, that's the absolute key to reliability and performance.